This is Unit 3 Factoring Review from the Quarter 1 Assessment Review for Advanced Algebra 2. So objective 3.1 is to factor each polynomial completely. So number 1, the first thing you should always think about is there a GCF? This problem does have a GCF, and that is 5. When I factor out the 5, I end up with x squared minus 25 w plus 7 squared. Now what you should think when you look in the parentheses is this able to be factored more? Because you have two terms, your options are difference of two squares or sum or difference of cubes. In this case, we have a difference of squares, both perfect squares with a minus sign in between. So what I'm going to do is take the square root of each part and then write them in the form a minus b and a plus b. The square root of x squared is x, minus the square root of 25 is 5, and the square root of w plus 7 squared is w plus 7. The second parenthesis will be the exact same, just with a plus sign, x plus 5, w plus 7. And then don't forget your GCF at the beginning. And then to finish it off, you need to distribute and simplify inside the parentheses. So if I distribute, I end up with x minus 5w minus 35. And on this one, I end up with x plus 5w plus 35. And again, don't forget your GCF in the beginning. So your prime factors for this problem are as you see right there. For number 2, again, you should always be thinking, do they have a GCF? Again, the answer is yes, they do. They all have an A in common. They also all have a B in common. So when I factor out the A, the lowest exponent is just 1, so I just factor out 1A. Same for B, the lowest exponent is just 1, so my GCF is just AB. When I divide each term by AB, I end up with a squared b to the third plus ab squared minus 1. Remember, when you divide out everything, you end up with a 1 because a number over itself equals 1. This is a trinomial, but it's not in quadratic form, so there's nothing else we can do in this problem. It was simply a GCF problem. That is your final answer. For the next problem, the first thing I think of is, does it have a GCF? And the answer is no, other than 1. The second thing I think is it in quadratic form? It is a trinomial, so is it in the form ax squared plus bx plus c, or is the middle exponent half as big as the larger exponent? Again, the answer is no. It is not in that form. So because it's a trinomial with no GCF and not in quadratic form, then that is prime. There is no way to factor that trinomial. Moving on to number 4. The first thing you always think is, does it have a GCF? But in this case, the answer again is no. However, this time there's 1, 2, 3, 4 factors. So because there are 4 factors, you can solve this by grouping. Group the first 2 and group the last 2. The GCF in the first group is x, y. When I factor that out, I end up with 2 minus x. The GCF in the second group is negative 3. It's negative because the first term is negative, and 3 is your GCF. When you divide by negative 3, you end up with 2 minus x. Because the inside of the parentheses matches 2 minus x, that is one factor. And then the outside is the other factor, so xy minus 3. Always check your factors at the end and make sure you don't have any GCF or difference of squares. And I do not have either of those things, so I have prime factors. That's my final answer. On number 5, again, we start by thinking, does this have a GCF? And this answer is no, it does not have a GCF. It is in quadratic form, so I can factor it. It's a trinomial. Because I have an a other than 1, I start by multiplying. 3 times 4 is 12. So I need factors of 12 that add up to 8. Those factors are 6 and 2. 6 times 2 is 12. 6 plus 2 is 8. So I bring down the first term, 3x squared. I split the middle term into two terms, 6x plus 2x. And then I bring down the last term, which is 4. Now I have turned it into a grouping problem, so I will group the first two and group the last two. The GCF of the first two is 3x. When I factor that out, I end up with x plus 2. The GCF of the second term is 2. When I factor that out, I end up with x plus 2. Because my parentheses match, x plus 2, that's one factor. And then the GCFs on the outside is the other, 3x plus 2. I do not have a difference of squares or a GCF in either of my factors, so it is complete. On number 6, I again do not have any GCF, but I do have a trinomial. Because I have a trinomial, I have to check, is it in quadratic form? Well, the middle exponent is 1, the bigger one's 2, so therefore it is in quadratic form. So in this case, I'm going to call my a x minus 4. So I'm going to rewrite that as 3a squared plus 5a plus 2. Now I'm going to factor it like a regular trinomial. 3 times 2 is 6. Factors of 6 that add up to 5 are 3 and 2. 3 plus 2 is positive 5. 3 times 2 is positive 6. Bring down my first term, 3a squared. Break up my middle term into 3a plus 2a, and then bring down my last term, plus 2. Because it's 4 terms, I can group, so I'm going to group the first two and the last two. The GCF in the first group is 3a. When I divide that out, I end up with a plus 1. The GCF of the second group is 2, and again I get a plus 1. So my two factors are a plus 1 and 3a plus 2. Now I'm not quite finished because I need to plug in x minus 4 for a. So everywhere I see an a, I'm now going to plug in x plus 4. And then I need to simplify that. So the first parenthesis, all I have to do is add the 4 and the 1, and I end up with x plus 5. For the second parenthesis, I distribute, and I get 3x plus 12 plus 2. And when I add 12 plus 2, that gives me 3x plus 14. Neither of my factors have a GCF, and neither one is a difference of squares or cubes. So those are my final two answers. Moving on to number 7. The first thing we think is, do we have a GCF? The answer is no. This is also in quadratic form, but I don't have to call x squared a in this case since I'm going to use the grouping method. I just have to be careful when I make my groups. So to start, I'm going to multiply 2 times negative 5. That gives me negative 10. Factors of negative 10 that add up to 9 would be negative 1 and positive 10. Negative 1 times 10 is negative 10. Negative 1 plus 10 is positive 9. Then when I set up my grouping, I just have to make sure that I write it exactly how it is. So the first term is 2x to the 4th. When I break up the middle term, I'm subtracting 1x squared because my middle term is 9x squared plus 10x squared. And then I'm going to bring down my minus 5. Now I can do grouping. The GCF in the first group is x squared. When I factor that out, I get 2x squared minus 1. The GCF in the second group is 5. When I factor that out, I get 2x squared minus 1. So my factors match. Therefore, I get 2x squared minus 1 is one factor, and x squared plus 5 is the other. Now I have squares in my answer, so I need to double check. Do I have a difference of squares? The answer is no, because 2 is not a perfect square, so that factor is complete. And for the second one, two things happen. We have a plus sign, so it cannot be a difference of squares, and 5 is also not a perfect square. So these are the final answers. The next problem, I need to look for a GCF, but there is not one. But I have a binomial, so it's either a difference of squares, it's not a difference of squares because it's a plus sign, or a sum of cubes. Well, x cubed and 125 are both perfect cubes, so it is a difference of cubes. So I take the cube root of each part, that's my a and b. The cube root of x cubed is a, the cube root of 125 is 5, and then I can write my form. Don't forget SOAP, that talks about your signs, same, opposite, and always positive. So the first parenthesis is a binomial, and it's just the the cube roots with the same sign as the problem. So I get x plus 5. Then we square x, so that's x squared. The opposite sign of the problem is minus. Multiply a and b, so that's 5x. Always positive, square b, and get 25. That is completely factored. Notice a difference of cubes, you end up with a binomial times a trinomial. So be careful when you have a difference of cubes, that's how it should look at the end. Looking at number 9, we think, does it have a GCF? And in this case, the answer is yes. The GCF is 3. When I factor that out, I get x to the third plus 27. That is a sum of cubes because x cubed and 27 are both perfect cubes. So I can take the cube root of each part and continue factoring. The cube root of x cubed is x. The cube root of 27 is 3. So I'm going to bring down my GCF of 3. My binomial will be x plus 3, same sign as the problem. Then square a, so that's x squared. Opposite sign of the problem, 3 times x is 3x. And then square b, which is 9. And now it is factored. The next problem, number 10, is a difference of squares. There is no GCF, but they are both perfect squares. Because they're perfect squares with a minus between them, remember the form is a minus b and a plus b. So the square root of 36 is 6. The square root of x squared is x. So I have 6x minus x minus 4. And then 6x plus x minus 4. For the first one, I need to distribute the negative. So that gives me 6x minus x plus 4. And then I get 6x plus x minus 4. And then I just combine like terms. 6x minus x is 5x, so I get 5x plus 4. 6x plus x is 7x, and then minus 4. And those are my final two answers. For number 11, this is another quadratic form problem. So I'm going to call A x minus 2. When I do that, I can rewrite this as 3a squared minus 3a minus 10. So I need to multiply the 3 and the negative 10. I get negative 30. So I need factors of negative 30 that add up to negative 3. So start with 1. 1 and negative 30. That does not add up to 3. 2, negative 15. Again, not adding up to negative 3. 3 and negative 10. Again, does not add up to negative 3. 4 does not divide evenly into 30. So skip to 5. 5 and negative 6. That does not add up to negative 3. And then I'm at 6 and negative 5, which I've already pretty much done. When I kind of get to the same numbers again, I know I'm finished. Well, there are no factors of negative 30 that add up to negative 3. If that's the case, that means it is not factorable. So therefore, this problem is prime. For number 12, again, we have a quadratic form.